Okay, let me quickly introduce our first speaker. We've been having talks from all around the world, and this time we have Professor Bill Chen all the way from China, and he's going to talk to us about some experimental mathematics. Please, Professor, go on.
Okay, thank you. 开始啊，我第一页。Hello, everyone. Good morning, good afternoon, and good evening. I feel deeply honored and humbled to be given this prestigious opportunity to report on some simple and naive observations and questions which came up when I tried to play with Maple without a specific purpose. So I must say thanks to the organizers for their courageous invitation. First, let me start with the classical q-Catalan numbers. The first time I tried to plot a function using the Maple plot command, besides the examples in the manuals, the function that came to my mind was a q-Catalan number. That's a q-Catalan number. Although the q-Catalan numbers are familiar, the shape of the curve is still worth looking at. So here is how it looks. Using Maple, we compute and plot the q-Catalan numbers as a polynomial for n equals 12. So that on the right-hand side, that's how it looks. So this actually is this is a plot that gives a global impression about the polynomial. What can we say about these polynomials? To get a better picture, let's plot for the range q from -1 to 1, within room in to see what happens. So here is the observation. The figures suggest that the q-Catalan number Cnq is positive for all q, and furthermore, it's convex. So the convexity is equivalent to this condition. The second derivative is non-negative. Maple gives actually more evidence. Now, here is the figures. We don't have to say anything. It's worth more than 1,000 words. So here are the figures. So this says that actually the figure says indicates that the second derivative is not only positive but also convex, and we can continue to consider the fourth derivative, and we still get a convex curve. So formally, we call a function totally convex if the derivative of every even order is non-negative. That is, that's it. At first glance, I thought that it should be an easy fact. When Teddy Andy Burhan visited me in the summer of 2016, he made some efforts in trying to prove it, but he did not get it right at that moment. Recently, he and Stephen Wagner settled the main case. Namely, Cnq is indeed convex, but the general case for higher orders remains unsolved. Here is a remark. As mentioned by Andy Burhan, Wagner, their proof stands as highly technical, And they hope to see a more concise proof. Since this has already been pointed out by the authors, I will not dwell on it here. Notice that the figures seem to tell us that the higher order case might be easier since the minimum value appears to get bigger and bigger. It puzzled me why a combinatorial polynomial has such a simple analytical property that is not so trivial to justify. Maybe you have missed something, and I believe that this is likely to be the case. For q-Catalan numbers, we may consider the unimodality of the coefficients. It turns out that we conjecture that the coefficient, or we observe that the coefficients of q, or the powers of q, or the coefficients of q and the two special coefficients are 0. So we accept the first and the last two terms, the coefficient sequence is conjectured to be unimodal. Moreover, after excluding a certain head and tail, the remaining sequence is conjectured to be log-concave. That observation was made about 20 years ago. Actually, for a pair of non-negative integers, we define this rational q-Catalan functions as this. And also, these two people, Xing and Zhong, conjecture the parity unimodality of this polynomial. That means this even coefficients, the even powers, the coefficients of even powers form a unimodal sequence, as well as the coefficients of the odd powers. Let's move on to the stronger properties that log-concavity. Richard Stanley wrote a classical survey on the log-concavity. I think everything, you can find a lot of background there. And for q-Catalan numbers, the log-concavity is not obvious, or it's not universally, not generally true, but essentially true, as we conjecture. Here we consider the sequence, the bk, that's the sequence we wish to prove to be non-negative for the log-concavity, and consider this sequence bk. And here is a plot. And you see this bk, the coefficient bk, seems to be log-concave. And also, but we have something beyond our expectation. Even though the coefficients bk are not log-concave or unimodal, but we see that there is some kind of alternating property. So the coefficients are alternating, and it's getting the differences, or the range is getting bigger and bigger. The vibration gets bigger and bigger. And this is something we didn't expect to discover, but which seems to be important, to be an important property. And even more, that's something we didn't expect, which we can state quite clearly, quite neatly. And computation suggests that the head and tail are unimodal with respect to parity, and the sequence formed by the coefficients. The even powers is log-concave. If we consider the even powers, and we just get this like an ordinary sequence of log-concave sequence. And I think there might be some hope to prove it. And we have already considered the normal distribution of the coefficients, but now we have higher order kind of normality, normal distributions. If we consider coefficients B sub k, and we still get the normal distribution. And we see that we observe that there is a higher order normality involving the coefficients. More precisely, computation indicates that the limiting distribution of the coefficients, that pk, is also normal. And interestingly, an AI-assisted proof of the above observation has been obtained by KCG. It's also shown that the limiting distribution of the coefficients of the higher order, that pk, is normal for any non-negative R. So I'm really impressed by the power of AI assisted proofs. So it works in this case, which does not seem to be obvious to me. And besides the log-concave sequence, or the pk, and we can consider the higher order to run inequalities. So these inequalities can be thought as a higher order counterpart of the Newton inequalities. Now we give for polynomial AQ. Now we consider the transformation of another the two-run coefficients or two-run transformations. Here we define pk as this kind of transformation from the coefficients ak. Okay, so and even for this transformation, to run transformation of the q-Catalan numbers, and we still get a normal distribution. Another candidate, recently we studied the Ramanujan polynomials. Those polynomials were introduced by Ramanujan in two seemingly unrelated contexts. They turned out to be related to the enumeration of rooted trees with respect to the number of improper edges. For the combinatorial background, an insertion algorithm independently devised by Shor and Dumont has played a vital role in the combinatorial study of these polynomials. Recently, we developed a grammatical calculus for those polynomials. Now that R and can denote the number of rooted trees, something like that. And we define the polynomial R and U as follows. And what can we say about this polynomial? And maple computation suggests that the limiting distributions of both this polynomial and the log-concave transformation are unimodal, or not are normal. The limiting distributions are normal. Actually, even for the two-run transformation, we get a normal distribution. And for the q-binomial coefficient, the second, the classical combinatorial objects that we're going to consider is the q-binomial coefficient, or the q-binomial coefficients. What can we say about the q-binomial coefficients beyond the classical result on unimodality? Like the computation for the q-Catalan numbers, computation suggests that further properties for the coefficients of the q-binomial coefficients and their log-concavity transforms. And King Ono has a recent paper on the log-concavity behavior of the q-binomial coefficients. Now, Maple's computations lead to the following observations. For large N, the head and the tail of this log-concave transform of these polynomials are alternating and unimodal with respect to parity. Roughly speaking, these q-binomial coefficients are reluctantly log-concave or gradually log-concave. The coefficients or even powers of this log transformation are unimodal and essentially log-concave. And for k and n minus k tend to infinity, the limiting distributions of the log-concave and the to-run transformations of the coefficients are normal. And here is just figures. Actually, this kind of alternating property of this log-concave transformation, that's beyond my expectation. And here we have this kind of, it's alternating all the way around, all the way, but now when n gets bigger, so it gets more streamlined. Okay, here is a distribution, alternating property, and the even powers. And we wouldn't like to mention that Canfield, Jensen, Zellberger proved a symptotic normality for the Mahonian statistics on multisets for permutations. Also, Binney, Konvalinka, Swanson studied the major index distribution on standard Young tableau of arbitrary straight shape and certain skew shapes, generalizing the previous results of Canfield and myself. Now, when we come to unimodality as a possible approach to the log-concavity observation concerning the coefficients or even powers in the q-binomial coefficients, we should not forget the classical argument of Sylvester using invariant theory. As a matter of fact, we do not really have to get into invariant theory. The key gradients are a pair of differential operators on polynomials in A0, A1 to AN together with an identity of Kelly. So consider the following two differential operators. We have this one, and we have this Kelly's identity on these operators D and delta. And actually, I think this identity is also related to the work of Richard Stanley on differential posits. Without the background of invariant theory, but of course it is related. And Hilbert's identity is an operator identity just on polynomials without getting into invariant theory. So this is an independent operator identity. So Hilbert's identity reduces to Kelly's identity when applied to semi-invariants. A combinatorial proof of Hilbert's identity and an account of Sylver's proof can be found in the paper of mine with my co-author. So this is also, now we come to another classical combinatorial object, the q-derangement numbers. The basic idea is to give an involution setting for the q-derangement numbers. So for the classical case, let En be the set of permutations in which each fixed point may be endowed with a minus sign. Assigned fixed point is denoted by bar, I bar. Like 4 is a fixed point, but has a bar. 2 is a fixed point without a bar. So this is a kind of, En is a kind of extended set of extended permutations. And now we use E sub nk to denote the permutations with exactly k minus fixed points. Now this is, so we just, this is a really an example I use in undergraduate course to give the students an example of the idea of involutions. And there's a trivial involution. So consider a subset of En consisting of permutations with at least one fixed point, signed or unsigned. Let I be the minimum fixed point. We change the sign so that we have a sign reversing involution. After cancellation, only ordinary derangements remain, so we get this classical number. And interestingly, the definition or the object of extended permutations with fixed points can carry a minus sign. This structure has appeared in the following two papers. And then we can move on. How can we get to the, can we have this q derangement, a similar setting for the q derangement numbers? And it turns out this seems to be the case. And with respect to the natural order, and the computation suggests that we have this kind of, this formula. And for this formula, Kai-Sun Yang gave a proof using the four-top bijection. And Peter Gore gave a proof using Stanley's theorem on P partitions. So there should be, now we see that we by some computation, we found there should be a sign reversing and decent preserving involution on G, where the sign over permutation is defined as a product of minus signs. So this seems to be, but this, the computation can be justified. KCG found an AI-assisted construction for sign reversing a decent set preserving involution, which is based on the shuffle theorem of Wax. So we may say that there is an involution setting for the q derangement numbers. Infinite log-concavity. Now we have one question here. Defined, this is infinite. We don't have to get into the definition here. And the question is, numerical evidence suggests that the product of two infinite log-concave polynomials is often infinite log-concave. It's not generally true, but there are some counterexamples. But the question is, we still have the question, can we find a good or natural conditions for which a product of two infinite log-concave polynomials remains infinitely log-concave. And also we have, in this regard, we have another question. The limiting if we consider the number of permutations for which the longest increasing subsequences are of non-scale. So the limiting distribution of P and K is the Tracy-Widom distribution. It was observed, or it was noticed that where the computation shows that for N is, in general, the sequence is infinitely log-concave. And this, now the last combinatorial object is a cumulative partition function. There are good reasons to consider this function, and Richard Stanley has a paper related to this cumulative partition function. But unlike most partition functions, we have not found simple congruence relations on arithmetic progressions, namely the congruences of the following form. So now we conclude with the key question, to be or not to be. That is there a non-existent theorem in general, or are there some congruences in particular? So it's up to you to give the answer. Now we come to the last page. In this virtual event, I'd like to virtually thank you for your virtual attention. Thank you all.
Thank you. Thank you, Professor. Wonderful talk. Are there any questions, comments from the audience? Adam, yes.
Yeah, thanks. Thanks for the lovely talk. I guess I was especially interested in this idea of unimodality with respect to parity. And I guess I'm wondering if you can say, are there any new techniques that are available for proving that when it's observed, or any better understanding of when that should arise as a phenomenon?
I have no idea except for the known techniques, because I think to prove the coefficients of the even powers from a log-concave sequence, we can only think of the previous techniques. But now I have no idea about any new possibilities. Thank you.
Okay, thank you. Yeah.
I wanted to ask more or less how the proof, when proving that the coefficients have like a normal distribution, more or less what is the flavor of that proof?
And for the classical case, we'll have to use Bernoulli numbers, some inequalities. But for the general case, the higher order, KCG found a kind of AI-assisted proof. I have not examined her AI-assisted proof. Okay. But I can only think about the inequalities or some generating functions. But I didn't expect to have this higher order, some kind of normality or normal distribution of the let's say, log-concave transformation of the coefficients. That's came up only in the computation. Thank you.
Thank you. Any other questions? Okay. If not, let's thank the speaker again for wonderful talk.
Thank you.